So I'd love to talk to you all today about how to solve on-chain data leakage and add privacy using something called Fully Homomorphic Encryption, which is a special type of encryption that allows you to do computations or run smart contracts on data while the data still remains encrypted and therefore confidential and private. But before that, I wanted to give a quick introduction to myself. I worked for 10 plus years in blockchain and privacy technology. I also lead up the technical steering committee at Decentralized Identity Foundation. And I have joined Zama very recently to head up the Zama developer platform, which is going to be the managed API service that Zama is launching later in the year. So to get started, maybe, why do dApps need privacy? On-chain data is public by design, and that makes it hard to build dApps that require confidentiality. And the current reason for that is because you need to be able to see the data to verify the state and ensure that the state on-chain is correct. But obviously, this comes with a lot of challenges. If you want to build a use case that requires more confidentiality, you cannot do that on a lot of public blockchains at the moment. What Zama enables is building confidential blockchain applications on any blockchain. And the way that it sort of achieves this is without compromising any verifiability or composability. The encrypted computations that you have remain publicly verifiable and publicly auditable. The security that is added means we use fully homomorphic encryption that ensures the encrypted data remains secure at all times, including when doing the computation. And it still has composability. So you can still mix data and multiple users and compose smart contracts without losing any of the benefits that you might already have from a language like Solidity. And there's a bit of distinction between confidentiality versus privacy, because confidentiality relates to the obligations of those who manage information. And privacy is about the rights of individuals. Both have something in common, though, which is to protect sensitive information. What does that mean in practice? In practice, it means use cases like tokenization, where you can manage or swap tokenized assets without other people being able to see the details behind what those assets are or the values of those assets. It includes things like private transfers. So, for example, if you send a stable coin to someone, you want to use public blockchains for that, because it adds all of the benefits that public blockchains bring, while being able to keep the balance amount or the transfer amount private and only accessible to the sender and the recipient or any other authorized parties. You can do things like blind auctions. You'll see some people already starting to build this in the Zama community, where you can bid on items without revealing how much is everybody else bidding, and thus making the bids a lot more fair. Or confidential voting that prevents bribery or blackmailing while keeping votes private. It's only at the end of the voting period or at the end of an auction that you can reveal who the winner is, maybe even without necessarily revealing the characteristics of, like, who else bid how much amount in that particular auction. So it unlocks a whole range of use cases where people would want to use public blockchains, and they want to use the composability of public blockchains, but they require privacy, which is the rights of the individuals, or the confidentiality, which is the sensitive commercial data that a dApp might want to keep private from other people from being able to see and understand. So how does this work? We are building something called the Zama protocol. The Zama protocol, what makes it unique is it has that, as previously stated, the end-to-end encryption, composability, and cross-chain support that allows encrypted data to move seamlessly across multiple blockchains. And the architecture of this is designed using 4 different components, which I will talk about later in the talk. But we call this FHEVM because it's FHE for fully homomorphic encryption, and EVM because it's on an EVM sort of execution layer. The 4 different components that we go and support is host chains, where the smart contracts run, co-processors that perform the FHE computation, gateways that coordinate the protocol activity, and KMS for managing secret keys using multi-party computation. By the way, if at any point people have questions, feel free to stop and ask, because I don't actually see the chat window while I'm presenting my screen. So before I sort of dive into these specific components, one of the things that makes fully homomorphic encryption, or FHE, quite different from other technologies like ZK is in FHE, the confidential data remains on-chain, but in an encrypted state. Whereas in a lot of ZK-based methods, what you're doing is you're doing the proving on the client side and maybe only writing ZK proofs onto chain, but the data itself remains off-chain. So one of the advantages of FHE, as we see it, is the fact that the data availability does not go away. It's still present on-chain. To achieve this encryption, you have FHE keys. Similar to, we'll dive into the types of data that we talk about, but you have public keys and private keys that are related to various different data types. And in terms of the architecture, what you have is you might have a DApp front end that is calling a smart contract, which calls a specific FHEVM smart contract. The computation related to that is run by the FHE coprocessor. And then decryptions or re-encryptions are handled by the gateway. So what does the host chain have to do? The host chain is, it works out of the box with any Ethereum or EVM compatible chains. You're not going to be running your DApp on a Zama chain or a Zama protocol chain, which means there's no fork or protocol change required. You can run all of the, you can continue running your smart contracts, let's say on Ethereum, Base, Polygon, etc., etc. The integration with those contracts is using a Solidity library called FHEVM. And instead of using the traditional data types that you might be used to in EVMs, we created encrypted types that have close equivalence to all of them. So for example, we'll dive in a bit later into this, but you have things like, instead of unsigned integer 64, you have encrypted unsigned integer 64. Or instead of Boolean, you have encrypted Boolean. The Solidity library that we have has FHEVM smart contracts, and we partner with trusted sort of companies like OpenZeppelin to create basic sort of smart contracts or libraries that you can use within your application. And just to highlight, some parts within the code, if you're programming in Solidity, you might be using uint64. Instead, you will use euint64. So a lot of the structure of the contract remains very, very similar, and you can reuse sort of similar smart contracts as you have already developed. And so looking at the encrypted types, you have things like encrypted addresses, encrypted booleans, and many different kinds of encrypted signed or unsigned integers. In terms of gating access to who has access to that data, you have access control logic that you can embed, and the access control logic in FHEVM is programmable. So this allows you to define who is allowed to decrypt or interact with the encrypted states, and the logic is directly written into the smart contract on who's allowed to do that. So in the code example that you see this interface called FHE.allow, and FHE.allow is prescribing that the message sender is able to decrypt or interact with that encrypted state. But what does actually do the job of the coprocessor? So this does not run on the host chain. This does not run on Ethereum layer 1 or Base or Polygon or wherever your smart contract is deployed, because this is highly specific kind of cryptography. We have something called a coprocessor execution. So on the host chain, you will write something called the confidential smart contract. You then have the FHEVM contracts that emits events that we listen to, or the Zama protocol coprocessor network listens to. And the event listener then actually carries out the execution and stores the results to be fetchable. Coprocessors listen to these events from many, many different host chains, and then send the result to the gateway, and the gateway reaches consensus on which of these answers is valid. The coprocessor is not a single unit or service. This is also run using multi-party compute. The gateway is a protocol coordinator. In our case, the gateway is deployed as an Arbitrum layer 3 rollup. You don't deploy smart contracts there. The only smart contracts that are deployed are the ones that are related to coordinating all of this interactions and transactions that are happening between the coprocessor, the KMS, and the host chain. So just taking the example of a view from a user, the user has interacted with some sort of smart contract, which emits events that are listened to by the coprocessor, and the results are then submitted to the gateway. When the user then wants to fetch the results or decrypt the results, they submit zero-knowledge proofs to prove that they have access to that particular result, and then the gateway rollup does the act of fetching and providing them the decryption of that particular data. It can also do the work of requesting the cipher text to be bridged from one chain to another. User decryption is probably the main way in which users will see this, which is they will receive the on-chain handle or the on-chain address related to the ciphertext, and they can request decryption of the ciphertext that is associated with the handle by making a function call to the gateway. The gateway validates the request, and it forwards it to a KMS system to request decryption of that data. On the encryption side, so how do you initiate a transfer? So what you have is the user encrypts the input with a zero-knowledge proof of the plain text and submits it to the gateway. The coprocessor listens for those events and returns signatures upon successful validation of that. And the user submits their transaction along with the input handles and attestations. This is what allows the coprocessor in the later stages or during the execution of a smart contract to be able to go and decrypt the data. And then finally, we have a threshold key management system. So the idea behind the threshold key management system is the FHE key across a host chain or many other host chains is a single key. It does get rotated and changed over time, but in any sort of like singular period, the key is not kept in as a single key. The key is split up into shards, and the Zama protocol uses a threshold decryption protocol that is powered with multi-party compute. And so no single node ever has the full key. And the decryption results are only done by reconstituting the key across multiple KMS nodes. So in our protocol, we have 13 different KMS node providers and 3 co-processors, or 3 operators of co-processors. All of them are independent. So there's one sort of KMS node, for example, that is run by Zama, but the rest others are other highly reputable multi-party compute operators and actors. So what's next? We have launched on testnet today, and we have support for Ethereum Sepolia. Other host chains will come later in the year. And after being able to test and validate things on Ethereum Sepolia, we plan on launching on mainnet at some point, I think in September, October, and then add support for other EVM chains. Solana support is also within the roadmap, and we plan on adding that some point in the first half of 2026. So one thing that you might have heard of with fully homomorphic encryption is that it is slow. And Zama has been spending years and years of R&D and research into making this faster. So at the current benchmarks, FHE is fully fast enough so that if every single block on Ethereum was filled with an FHE transaction, the Zama protocol network would be able to fully handle all of that traffic. Why is FHE slow? To give an example, it's because of the special sort of like, properties in fully homomorphic encryption. If you have something, say, like 1 megabyte of data that is unencrypted, when you put it into an FHE context, that might grow to something like 100 megabytes or 200 megabytes. Now, for most smart contracts, you're not talking about megabytes of data, you're talking about bytes of data. So that growth is manageable. But to make the FHE execution fast and be able to scale with a lot of different host chains that we want to add, there's a lot of different techniques that Zama protocol uses. Part of this is parallel execution. So the computation graph and running it is done concurrently across many different co-processors, so you're able to split up the tasks. We also use hardware acceleration, which uses GPUs to achieve sub 20 millisecond latency across many of the core sort of arithmetic tasks that are happening across the various different encrypted data types. And there's horizontal scalability, which allows splitting up those tasks as well. The upshot of that is by 2026, which is next year, we believe we'll be able to do hundreds of transactions per second, and within the next couple of years, be able to do tens of thousands of transactions per second. The current sort of benchmarks that we look at and being able to run that for Ethereum sort of mainnet, we are able to do even just on CPUs, and being able to accelerate that in time for the mainnet launch using GPUs. Then you might have heard of something called FPGAs, which are field programmable gate arrays. FPGAs are a type of electronic circuit that allows you to create or prototype new chips. And so this would be custom designed to do FHE calculations. That would allow us to accelerate a lot of those numbers by 2026. And by 2028, we think we can take or we have the target of taking those custom chips that have been designed using FPGAs to something called ASICs. ASICs, in a simple sense, they are custom CPUs that you can design to run specific types of operations or specific types of calculations. Any questions so far before I dive into maybe an example contract on any of the stuff so far?
I think it's going great. If there's any question in the chat, I'm going to just raise my hand and ping you there. Perfect.
Okay. So the example that I want to give is of a confidential ERC20. This is something that we developed in partnership with OpenZeppelin, which you might know as a creator of many standardly used smart contracts and libraries. The confidential ERC20 standard has been submitted as well as an ERC of its own. And so it applies and works with, so before I go on to that, this is maybe a bit of background. So it will be its own ERC called ERC 7984. And the idea behind that is to create a new standard that is composable and similar to ERC20, but for confidential tokens. And the technology behind that is open enough so that you can be using any type of encryption technology. There are many other participants in something called the Confidential Token Association that Zama is one of the founding members of. But it doesn't necessarily need to use fully homomorphic encryption. Some of the members in the Confidential Token Association have used other types of technology for this. So in the confidential ERC contracts, you can also put in conditional logic. So you can use, for example, a select statement that provides a encrypted Boolean resulting from a comparison, and then the value to return if the condition is true, or a value to return if the condition is false. To take an example of this, and I'll provide links at the end, for a confidential ERC20 transfer, you can see a similar function transfer with the address to transfer to, the encrypted amount, and the input proof that will be provided by the user, which I sort of referenced at the beginning. And then you can check if the user has a sufficient balance. The return type on that is as an encrypted Boolean. So you're able to compare the amount to the sender's balance without actually knowing the balance, and then calculating the actual transfer amount if the value is transferable, and then updating the balances as you go along. So very similar to how you might do in a confidential sort of an ERC20 contract, except in this particular example, the balance itself doesn't become known or published on the public blockchain. If you want to find out more, and I can run people through the light paper as well that we've published, you can check out the QR code that is available here, and the Zama protocol docs. The light paper and the white paper go into a lot more technical detail. Obviously, happy to talk through any aspects of that which people might want to run through today. But in overall, we are live right now on Sepolia Ethereum. My sort of like, team is working on managed APIs. So at the moment, you can use the SDKs that we publish to send and interact with these requests onto the Zama protocol chain on testnet. But in the future, we want to make that simpler and easier to do by essentially not having to run your own relayer or having to hold Zama tokens. You'd just be able to go sign up the same way that you can sign up to Infura, Alchemy, or any other such managed hosting provider like QuickNodes, and be able to send the user encryption and decryption requests that are necessary for FHE compute. That's it from my side. I actually was surprised by how quickly I ran through it, but I'm happy to take any questions.